Hello, welcome back. We're going to be reviewing the same diagnostic test, questions 14, 15, 16. I'm going to split up this one page, so I'm going to do on this video 14, 15, 16. The next one will have 17, 18, 19. Now, as I look at question 14, I notice it's another design question. So I'm just going to jot the word design above each of these design questions so I start to recognize them. So it says, when you double blind in a study, what does that mean? Well, I look back in my notes that I jotted down a really, really long time ago. And I say to myself, blinding is when people don't realize the treatment they're giving. So they might be getting Tylenol or aspirin or a Tic Tac. They have no idea what they're getting. They think that they're getting whatever medication, but they don't really know if it's the new one or the old one. Now, that Tic Tac idea, that's the placebo. That's a fake treatment. So that helps us decide if they just think they're getting a treatment, and really it's a Tic Tac. It's something that doesn't really have any medicinal purpose. And then last but not least, double blinding. So that's what we want to know about. So it says that's when both the person being tested and the person doing the study don't know. So that's the double idea. So as I look back on my answers, it appears that one is one person not knowing, and or selection A. B is another person not knowing, but that's not going to help me. I'm looking for two people that do not know. And so as I glance through my answers, it appears as if that would be selection E. So let me read that. It says, that's when I'm keeping the subjects from telling the researcher, no, that's D. I like E, to keep the subjects and the people measuring from influencing outcomes. So those are both people that don't know. So if I really like you and I'm the one administering the treatment, and I'm like, wow, I really like Steve. I want to make sure he gets better. I might not want to give Steve the placebo because I really want Steve to get some type of a medication that'll help him out. So to prevent that from happening, we want to make sure the person giving the treatment and the person receiving it don't know. That's the double blind. Next question, 15. Well, as I look at this question, I immediately say to myself, aha, this looks like a probability question. I'm calculating the probability of an outcome. And the other dead giveaway is it said, what is the expected winnings? So immediately I know to look in my formula sheet, I need the formula for the expected calculation in a probabilities problem. So I'm going to write probabilities. It's abbreviated there. And I look at my formula sheet and I notice they help me out. They call it E parenthesis X is mu. So whatever the expected value is kind of like our formula AP statistics. Whatever we expect to happen is what we would predict, and usually that's the average or the mean. If it's the population I'm talking about, that's mu, also the mean. And then the formula sheet tells me how to calculate that. It's the sum of X sub I times P sub I. So that sounds really fancy, but it's really just saying, what was the probability of getting outcome X? And then multiply that by however many outcomes you have. And then this symbol tells us, make sure you go ahead and add those up. So that's exactly what I'm going to do. I end up saying to myself, okay, what's some possible outcomes here? Either I'm going to win the lottery or I'm not. So it says I sold 100 tickets. So that means I'm only going to have a winner and a loser. So 999 people out of 100,000 are going to lose. So they're going to end up having negative $2, correct? Because it says I sold the tickets for $2. So those guys have an expected value of negative $2. Now, I also have Mr. Winner. So I'm going to add that. Mr. Winner, there's 1 out of 100,000 that's going to win. And he's not going to get negative $2. He's going to get $500. So when I crunch this in a calculator, I end up getting negative $1.50. And I think this actually makes sense. So we say to ourselves, if I play the lottery, I expect to lose some amount of money, but not all of my money, because on average, someone's going to win. So if you can think of it another way, if the winner shared it with everyone else, they wouldn't have all lost an average of $2 a person. They all would have, if the winner shared it with everyone else, let's think if everyone won the 500, but again, I have to divide that by 1,000 because I'm going to share it, then that means everybody would make back their 50 cents. And that's what I see here. We lose the $2 in the ticket price, but if the winner shared their winnings with all 1,000 people, then the winner would be sharing 50 cents with everyone. So we kind of think to ourselves, someone's going to win, and ultimately, on average, an average person's only losing $1.50. Let's do one more. Question 16. Every year, 50% of the students miss at least 3 days of school. Oh, that's a dead, that makes me think in my head, this feels like a probability problem as well. The reason is this idea of at least 3 days of school. When I hear that, I think about this idea of calculating complements. So I'm going to write probability on this question as well. So either you missed school or you didn't. And to miss at least 3 days school, I'm going to have to set up a table. So I have my x values. And once again, I have the probability of getting that x value. So the possible x values, I have not missing any, right? I have missing 1 day, 2 days, and then it says 3 or more. So I might miss 3 or more. So this encapsulates every possibility, every probability, correct? So now I say to myself, if I added all these up, it would have the probability of 1, because either you missed none, 1, 2, no days, 1 day, 2 days, or 3 or more days, and that's everyone included. Now, I'm feeling like a bins. The reason why I'm feeling like a bins, and that's called binomial CDF, is that this is definitely binomial. I had a success or failure. Success, I showed up to school. Failure, actually they flip it around in this question. Either you missed or you didn't miss. So that is binomial. That only has 2 outcomes. It's binary. You either missed or didn't miss. Is it independent? Now, for the sake of this question, I guess we're going to assume it's independent, although I think it does depend. If you get sick, you might miss 3 days in a row. We're going to assume independence. We have an N, so it says that we had 400. So we have an N. And S just reminds us this idea of success and failure. So either you went to school or you didn't. We're not allowing anything in between. The other thing is we have a likelihood of this outcome. And that's exactly what they gave us. They actually gave us a likelihood. We know the likelihood is, we're assuming the likelihood is even each time, even though maybe it wouldn't be. But let's assume the probability of this would be the same each time. So I know that this is 50%. So the probability of missing 3 or more is 50%, which means I know using the complement rule, the rest of these would be 50%. So I can use binomial CDF because I'm given all the information needed. So I go in my calculator and I type in binomial CDF. And I look at my screen there. So I'm going to go ahead and do that. I go to Menu, probabilities. This is a probability distribution. And I end up going to scroll way down, binomial CDF. So it says number of trials. We got that, 400. Probability of success. We got that. We put 0.5. Lower bounds. It shows here we got 216, right? 216. Upper bounds, we got 400. So they've asked us to quantify what is the probability that 216 or more would miss at least 3 days of school. So I end up getting my answer 0.06, excuse me, 0516. So once again, on your paper, if you missed this question, you're going to want to find this number, and N was 400. The probability was 0.5. The lower bound, we said, was 216, and the upper bound was 400. My answer, C, 0.06. Thanks for joining us.